a finite rotation in any one of these planes is built up of infinitesimal ones in a very simple way. Of course, any finite one is made up out of the infinitesimal versions. Through a very simple formula. So, that makes us wonder what fault did other planes do in the 3 dimensions. You didn't have to have x, y, y, z, it was just some choice you made. Suppose you rotated all your axes, then the meaning of xy plane will change, meaning of yz plane will change. What is wrong with those planes? They must all actually obey the same thing. There is no real difference. Okay. So we guess that in R3, okay, in the 3D carrier space, so it is only a limitation of the coordinate system that this is happening. So we consider, so for example, we have a plane defined by, we can define a plane by a unit vector normal to it. What do we expect for a finite rotation by angle theta in this plane? Of course, counterclockwise active rotation. In this plane, what matrix should we write? We have everything in front of us. We know Lx, Ly and Lz are like the quote unit vectors of rotation, and finite rotation for any one of them at least is given in this way. So what will happen for an arbitrary plane? Yes, you can guess. It is that let L subscript n cap be equal to Lx and nx plus Ly and y plus Lz and z matrix, right? And we symbolically write this as n cap dot L. Mathematicians will faint at this kind of notation, but it doesn't matter. They are not in this room. So the L's are matrices. They are not in any sense vector, but putting that arrow on top saves us a lot of writing. And yeah, really you have to see mathematics books to see how much they struggle to retain purity of language. But we can sacrifice language to just get on fast in life. So then R n cap of theta is simply equal to exponent of theta times n cap dot L, which is equal to 1 plus summation 1 to infinity theta n cap dot L to the power n over n factorial. There is, okay, so this is very clear, right? This, it's obvious that this is how it will work. There is one other aspect I didn't emphasize enough. Note also that this is about building up using infinitesimal infinitesimal actions, where group theory enters in a very substantial way. Recall e raised to x is also obtained as a limit n going to infinity of 1 plus x over n to the power n, right? Good old Euler formula. And therefore, say Rz, just to avoid writing too much detail, Rz is going to be equal to limit n going to infinity of 1 plus what was it, just theta times Lz. Yeah, we are writing this exponent now using this Euler version of it, 1 plus theta times Lz, and let us write the n below the theta to the power n. So Rz can also be written as this limiting operation, which amounts to infinitesimalizing theta. This is the delta theta, subdivided into n pieces, and building up the big one as a multiplication of 1 plus this, 1 plus this one, which is all a group multiplication. Okay. So it is by group operation that we obtain the finite group element from the small ones. So that is the important feature of this formula, and that this is a large number of group elements being multiplied, and of course limit being taken. And remember, we have said about Cauchy completeness. Any such, so you think of the sequence consisting of any finite n, and then letting that n to infinity, the sequence Rz superscript n, where you multiplied only up to n, but then you let limit of that sequence in the limit n goes to infinity, that should be contained within your set. This is the meaning of a continuum, of a compact set. So these groups are all compact sets, and because they are Cauchy complete, because they after all involve real numbers theta over n, and the reals are complete, so they are Cauchy complete. So what we have concluded is quite a deep result, which is that well, I didn't quite prove this yet, but so I'll put a star on it, can be entirely obtained from infinitesimal group elements compounded by group multiplication that is the entries of the matrices are from reals, of course, because they are real. Finally, we note the most important thing, that the entries are all cosine thetas and sine thetas, so they are all bounded. Is a compact now the star part. We have yet to prove, we saw L, X, Y, Z and L n cap, etc. But we need to see it more generally. So what is this next step? So we go back to the, so this part is clear, right, that this group is essentially built up. I mean, we conjecture, because this guess that what happened to any one plane should be true of any other plane. So that is a geometric intuition, not an algebraic one. But in any case, starting with that, we saw that at least for any given plane, we have a compact set of matrices representing those rotations. And now we want to see what really happens if you exponentiate n dot L. Okay. For Lx or Ly or Lz, we could just easily take square, cube and see what happens. What happens in general? Okay, this is not obvious. Also, we get to more general Lie groups where this is a standard feature. and this was my theorem stated in quote marks. All about finite from infinitesimal, whichever way you want to state it. But we now need to check, and this is a feature of common feature of all Lie groups. So now we go to the next steps, which is to check what actually happens if you take higher powers of something like n cap dot L. Generically what happens is that, so question, if I take L n1 theta 1 times L n cap 2 theta 2, do we have a easy formula? We know that this is not equal to L n1 cap plus whatever you want to call it. It is not some simplistic answer like that. Okay. There is this question of what happens if you multiply like this, and the answer has to do with a particular property of the L matrices. So we check what happens if we take these commutators. So what will happen if you do Lx Ly? Can you calculate? Yeah, good. So Lx Ly is equal to Lz, I think. You can check this. We will not spend time writing matrices here. And we can also see I suspect you have seen it somewhere, right? You have all done quantum 1. So that is okay. So we'll quickly see the analogy to the quantum mechanical L, which is R cross P. So similarly, we have Ly, Lz, Yz equal to x and Zx commutator equal to y. Turns out that this commutator algebra is what is going to save our day. This is because there is a Baker-Campbell-Hausdorff identity which goes like this. If I if A and A be commutator, i.e. a comma b equal to b comma a comma b equal to 0, then e raised to a, e raised to b, the product of the exponentials becomes e raised to a plus b plus a half of the commutator a comma b. So it turns out this is the first step. If this is not satisfied, if they don't commute, then you accumulate more terms in the exponent of a commutator with a commutator, b commutator with a commutator, etc. But the point is that because of the matrix exponent, the exponents are not going to add. That is the main thing. So if we know the algebra of Lx, Ly, Lz, and more general, I will just write and more general versions. So if we know the algebra of Lx, Ly, and Lz, and it is a closed algebra, then you can always exponentiate it and expect it to tally with your n cap notation. That a commutator algebra such as that of else which is closed closed in the same algebraic sense, that given n1 cap theta 1 and n2 cap theta 2, there exists n3 cap theta 3 such that exponent what did you say? Sorry. So, yeah, exponent n1 cap dot L theta 1 times, so group multiplication, where theta 3 will be some function of and of course similarly n3 x, n3 y, n3 z similarly functions of everything, of theta 1, theta 2. Right. So functions of theta 1, theta 2 and of n1 cap, n2 cap. So the parameter, there are effectively three parameters. There is a unit vector in 3 dimensions, so it has 2 parameters and there is an angle. So there are 3 parameters. This is 3 parameters. So these 3 parameters are functions of these 6 That is the statement. Okay. Parameters in but this kind of formula is available, and the existence of this algebra ensures the closure of the group, and it also ensures that any group element can be accessed by exponentiation. Elements can be recast in this form. Making group multiplication manifest. Group closure property. Group closure ensured. Okay, in this form. Good. So we have covered quite a bit of the ground. I could add a little bit in terms of geometry of this. Think of the group manifold, okay, all the points in the group. The group is a continuous group, so it is parameterized by continuous parameters, so it is some kind of a continuum. Of course, if you take 3 by 3 matrices, then there are, but it's an orthogonal group, so there are what, 6 independent entries, and so it's some 6-dimensional manifold. But the point is that suppose this is the identity in it, so this is our group manifold, and I have not defined manifold either. I'll tell you in a minute what that means, but you just think of the set of all the points that constitute the matrix group SO3. Then you draw a local tangent plane. Linearize it, linear approximation to it. Which is also the group algebra. So you can erect in it these unit vector, these vectors Lx, Ly, etc. I will draw only 2. So you know that when it is infinitesimal, there is a matrix available Lx in terms of which all x rotations, but we saw that I can now do n cap dot L. So this whole plane is parameterized by n cap dot L. Okay. And what our theorems are telling us is that I can map it to any other place I like. In the neighborhood of G, and the group structure essentially remains the same. Again, I can write it in terms of exponentials of, well, so I can reach G by using the tangent space at this, and the two tangent planes are isomorphic. Isomorphic copy of algebra at E. Didn't prove all that, but this is what geometrically it will come out. We have to show that after doing the exponentiation, you can still write Lx, Ly, Lz again in this location, which have it's just going to be a similarity transformation. We'll do some of it a little bit later. Okay, so I just want to get to another important practical group, but this is what roughly the picture emerging is. What we have proved so far is that using the algebra near the identity, I can reach any group element. And we have also checked that if I reach group element G1 and a group element G2, I can multiply them together to also reach it directly by another exponentiation. That picture I am not drawing here. But that this happens is yet to be proved. Okay. The other important, so yeah, the other important group is SU2. So note SO3 algebra can also be written using J equal to I times L. When we were simple minded, we tried to get out of complex numbers by picking out the real parts. Now that we get more advanced, we supply an I to make it complex, so that then Jx, Jy equal to I times Jz, etc., or we say Ji, Jj equal to I times epsilon ijk, jk. So just by complexifying, and actually it is obviously a real algebra, but I have now complexified it. It has certain advantages. So the Li are skew symmetric or anti-symmetrics. But the good thing about the Ji is that they are Hermitian, right? So Lx transpose equal to minus Lx, but Jx dagger is therefore going to be equal to Jx. because there will be minus sign from transposition of the real part and minus sign from the I being complex conjugated. So I will just get J dagger equal to J. So what is nice is that exponentiation of Hermitian matrices gives you unitary matrices. So it gives, now I will remind you a old theorem we proved for finite groups, that any group, any finite representation can be converted unitary. Any finite size representation can be made unitarized using the tricks of Schur's lemma. So here also, if we do this, then we obtain a unitary representation of the orthogonal group, and that takes us to the, so what's the time? 12:20. So that takes us to SU2 group. And as far as SU2 group is concerned, again we have to analyze matrices of this type. So I will just drop the answer by saying that just as finite R Z theta could be written in terms of LZ or JZ, we can write U Z theta, a unitary matrix, to be exponent of I times theta by 2 times the Pauli matrix Z. So I have made a big jump. We have switched to carrier space two-dimensional complex vectors, let us say Z1, Z2, and sigma Z matrix, of course, as you know, is 1 minus 1, and also we will use sigma X matrix, which is 0, 1, 1, 0, and sigma Z, sigma Y. This is the only one you have to remember with some care. There is minus I in the upper right corner. So we introduce matrices sigma X, sigma Y, sigma Z, and I claim that exponentiating them exhausts all of the group SU2. One is that exponent I theta by 2 sigma Z will turn out to be equal to cos theta by 2 plus I sin theta by 2. This is easy to prove because sigma Z square is identity matrix and sigma z cube is equal to sigma z, and therefore sigma z to the 4 is identity again. So this again gives you cosine and sine series, where cosine series will have coefficient just 1 because it will be either even, so sigma z to the 4 is again back to identity, etc. So we get that all the even powers will just have identity matrix and will actually have the fluctuating part because of the I that comes only in the, yeah. So because of this and because of the fact that I am actually taking I times sigma, so or I sigma z square is equal to minus 1 equal to minus of I sigma z to the 4th, okay, and I sigma z cube equal to minus times I sigma z. So we get the fluctuating signs because of the I introduced, whereas the Pauli matrices themselves are just not giving any signs in their powers. Signs come from the I. But once you do that, you get cos theta and sin theta series like this. And the other fact I was going to write was that the algebra is exactly the algebra we wrote. So we'll just end here for the time. I can maybe write over here. And 2 is that they obey this algebra sigma I, but you have to put this crucial factor half. Okay. Sigma j over 2 is equal to I times epsilon ijk sigma k by 2, which was exactly the algebra obeyed by the j version of rotation group. So we will stop here today and resume with SU2 groups and Lie algebras later.